All right, so in this section we're going to be talking about indefinite integrals, what they are, where they come from, how we evaluate them. So in the previous section, we discussed the idea of using rectangles to approximate the area between a function and the x-axis, and that was called our Riemann sums. The more rectangles that we used, the better the approximation will be. And so consider this notation right here. Remember, this is your sigma, and from k equals 1, which is your index, to infinity of a sub k, where a represents the area of each of the rectangles in a region. Okay, so that's from our Riemann sums. The idea of a region, the area of a region is the sum of the areas of the rectangles, and that's where this symbol comes in, because as you know from Algebra 2 and Pre-Cal, sigma is used to calculate sums, and this is the Greek letter sigma, which in the Roman alphabet, which is our alphabet, is the letter S. And S stands for sum, sigma stands for sum. So whenever you see this notation right here, it is asking you to find a sum. Now this notation says the limit as n approaches infinity of from k equals 1 to n, so this is going to be approaching infinity, of f of c sub k times delta x. Now, if you look at the graph over here, delta x will represent the small change of x between each of the sides of your rectangles. And so the distance from 0 to c sub 1 would be the first delta x. From here to here would be the second delta x. And for the sake of this problem, we are keeping delta x the same distance all the way through, so the rectangles have the same base on each of the rectangles. Now, f of c sub k, that is the y value at each of these sides of your rectangles. So f of c sub 1 would be the y value right here. That's going to give you the height of your rectangle, and this would be using a right Riemann sum. However, and that would give you an over approximation on an increasing function. However, what you want to think about is this limit as n approaches infinity, because as n approaches infinity, that means the number of our rectangles is going to get large and larger and larger, and as the number of rectangles increases, the base of the rectangle will decrease, because in order to get more rectangles in here, you'd have to have a very small base. Now, as that base gets smaller and smaller, then this over approximation doesn't really have an impact on it, because the over approximation actually is not going to be an over approximation at all. It's going to be the actual height of that rectangle, because this base area is so small. Okay, so all this says right here is that you're going to find the sum of all these rectangles, which is going to be an infinite number of rectangles, and the area of each rectangle is found by this formula right here. This is your height of the rectangle, and this is the base of each rectangle. And this would be c sub 1, then c sub 2, then c sub 3, so it just gives you the different heights of each of the rectangles all the way up to infinity. So this is your Greek notation, which is a limit notation for your integral. And this can also be used as a Roman notation using the letter S instead of sigma. They still mean the same thing. Now, this is called an integral sign, and an integral sign is really just an elongated S. So it's just an S that has been stretched out vertically to create this shape. This is called your integral. You're going to have a lower limit and an upper limit of integration. These are the x values that you are going to be finding the integral between. And the integral just means, for example, if I want to find the area between here and here, this would be your a value, this would be your b value, and the integral between here and here means you're finding the area between those x values and the curve and the x-axis. F of x, that's just from right here, that is the height of our rectangles, and then dx is the same thing as delta x, which is your base of your rectangles. Now, in your integral, this is called your integrand, and whatever your variable is right here, that's the variable of integration that you're going to have. All right, so let's continue with this notation right here. This notation is simply a notation. That's all it is. So it's just saying find the sum from this x value to this x value of this function. That's all that this is saying. And you find the sum of those rectangles, and this is your area of each of those rectangles. That's all this notation says. The question now is, how do we actually calculate the sum? If we don't have a graph or anything, we just have an equation, a function. How do you actually calculate the sum of the rectangles to give us the exact area instead of just an approximation? Okay, so what we want to do is develop a formula, if you will, or an understanding of what your integral is going to be finding. So let's take a look at this right here. Our task is to find the area of the green region between the curve, which is f of x, and the x-axis. So we want to find the area of this green region right here between this curve, which will be represented by f of x, and the x-axis. So we're going to start right here. We're going to let a of x represent that area, and that's the green area. So a of x is your green area, and that is the area under the curve f of x between 0 and x. And we're going to let a of x plus h, which is the area from 0 to x plus h, which is from here to here, that is our green area and the pink area combined. All right, so h is the distance from x to x plus h. H is this distance right here. So a of x plus h is going to represent that area. So when h is a really small number, we can consider the pink region a rectangle whose base is h and whose height is f of x. All right, so as you see it right now, this height is very much different than this height. And so the further apart these two values get, the more different they may become. But our goal here is we want to look at this h value right here becoming very small. And so when h becomes very small, this would move back in towards the x. And when it becomes so small in between there, this height actually approaches the same height as the other one. So that's going to give us the height of the rectangle being f of x. That means the pink area is going to be f of x times h. That's your h is your base, f of x will be your height of this. And again, that is when h is very small. Now the pink area can also be found by this right here, which is a of x plus h minus a of x. Remember, a of x plus h is the green and the pink area combined. A of x is the green area. So this is saying green and pink minus pink, and that would give us, green and pink minus green, and that would give us just the pink area. And the pink area we saw from the other slide that was f of x times h. So what that yields then is this equation, the area of the pink and green together, which is a of x plus h, minus the area of the green, which is a of x, equals the area of the pink, which when h is really small is going to be f of x times h. Now, when we say h is really small, mathematically what we are saying is that this is a limit as h approaches 0 of that equation. Now on this equation, we can divide h over to this side of the equation. What that gives us then is the limit as h approaches 0 of a of x plus h minus a of x over h equals f of x. Now, I hope by now that you recognize this as your definition of a derivative. And this would be the derivative of a. And so this represents a prime of x. So what that gives us then is this equation that the derivative of the area of our region that we're trying to find, the derivative of that area, is equal to f of x, the function. Now remember from Algebra 1, when you first started learning about equations will always stay balanced as long as you do the same thing to both sides of your equation. So what we're going to do is we're going to take this equation right here and find the antiderivative of both sides of our equation. What that gives us then is the antiderivative of a prime of x will equal the antiderivative of f of x. Now the antiderivative of a derivative is simply going to give you the original function, a of x, because an antiderivative undoes a derivative. It's kind of like taking the square root of a square or cubing a cube root. They undo each other. All right, therefore, what that gives us then is that this area that we were trying to find is equal to the antiderivative of f of x. That is what that area is going to equal. And that is the basis of what we're going to be finding. So when we see a formula like this right here, this is asking us to find the sum of the area of the rectangles where this is your height, or this is going to determine the height of each rectangle, and this is your base of the rectangle. So this right here is just a notation that represents the area between the curve y equals x squared and the x-axis. This is just asking us to find the area. Now from the previous slide, it said that the area is equal to the antiderivative of f of x. And this is f of x, so therefore we just need to find the antiderivative of this. So Antiderivative, let's think about this for a minute. If you have just x, and I want to know what is the antiderivative of this. Well, the antiderivative would have to have an exponent that is 1 larger than this exponent. So the exponent would have to be a 2. And then if I take the derivative of this, I need to be able to get this value right here. Well, if I take this derivative and I bring the 2 to the front, that's going to give me a 2x. But all I see here is a 1, which means I would need to put a coefficient of a half right here. Putting a half would be the same thing as saying this over 2. Therefore, the derivative of x squared over 2 is going to give us x. All right, so let's try x squared now. The derivative will have to have an exponent that's 1 larger, so x cubed. And once again, if I take the derivative of this, bring the 3 to the front, that's going to give me a 3x squared. I need a 1x squared, which means I would need to put a 1/3 for a coefficient right here. A 1/3 would be the same thing as simply dividing by 3. All right, let's do one more. If I put a 3 right here, then the derivative would need to be an x4. And when I bring this to the front to take the derivative, that would give me a 4 for a coefficient, but I need a 1. Therefore, I need to put a 1/4 right there, which is the same thing as dividing by 4. Now, what I want you to do is just a little inductive reasoning right here and looking at your patterns. So this exponent started with a 1 right here. Now, how does this exponent right here compare to this one? It's always 1 larger, which means to find your antiderivative, you're going to add 1 to that exponent. Now notice the comparison between that exponent and this denominator. It's always going to be the same. So the new exponent also becomes your denominator. So the antiderivative of x to the n is x to the n plus 1 over n plus 1. Now, we put this plus c, which represents a constant, because there could be some kind of constant out here, because when you take the derivative of this, it would become 0, which would still give you this as your derivative. So remember, this is just saying find the antiderivative of the function x to the n, because the antiderivative represents the area of the region between this function and the x-axis. All right. Now, this is called an indefinite integral because we do not have any bounds for this integral. There's no lower limit or upper limit. We're not saying we're going to find the area between x equals 2 and x equals 5 or anything like that. We're just saying, what is your area formula, or in other words, what is your antiderivative? All right, so if you take a look at the problems that we have over here, we are given the integral of x squared dx, which would yield x to the third over 3 plus c. We've already done that one. Now, the integral of 3 over x squared dx, we want to try to convert these things into x raised to a power. So this would be the same thing as saying the integral of 3x to the negative 2 dx. And the antiderivative of this then, well, if you add 1 to the exponent, that is going to give you 3x to the negative 1 over that new exponent. All right, so simplifying would give you negative 3 over x. This one you would want to convert to 2x to the negative 1/2 dx. And I want to just take this moment right here just to reinforce, you do need to put this dx on here. Dx represents the base of each of these rectangles. It may be a notation, but it still has a meaning in the problem, okay? Even though it's not actually part of the antiderivative. All right, so if we add 1 to our exponent here, you're going to get 2x to the positive 1/2 over 1/2. Now when you divide by 1/2, that's the same thing as multiplying by the reciprocal, so that would give you 4x to the 1/2. And I forgot plus c. Don't ever forget the plus c on there. That will cause you to miss your answers. Okay. The next one, you're going to rewrite this. Now, I want to do something here to show you how this works on this particular problem. If we rewrite this as x to the negative 1 dx, and we try to find the antiderivative, well, if you add 1 to the exponent, that would give you x to the 0 over that exponent, which is 0. Hopefully you see the problem here in that you cannot divide by 0. So that does not work. What you need to pay attention to is don't get so caught up in writing everything as an exponent, x to the n power, that you don't remember some of your basic derivatives. The derivative of what function is going to be 1 over x. And that derivative, that function, is natural log of x. So this is your derivative. Your antiderivative is natural log, because the derivative of natural log is 1 over x. Now there's something that we also have to put onto here, and that is that this is the natural log of the absolute value of x plus c. And you must always put that absolute value on there. Now the reason being is because if you think about the graph of 1 over x, this is what we are starting with. 1 over x is your parent function for a rational function. Now, the problem here is that with 1 over x, you can put positive values in for x, you can put negative values in for x. You cannot put 0 because there's a vertical asymptote right here. But you can put negative and positive values in for x. Your antiderivative is the natural log of x. You can only take the natural log of positive numbers, because the graph of natural log of x looks like this. You cannot take the natural log of 0, which was okay. We already couldn't take the natural log of 0. But we also cannot use the negative values that are on this function. We can only use the positive values. So the antiderivative of 1 over x is going to be natural log of the absolute value of x plus c. And you must put these absolute value bars anytime you find the antiderivative to be a natural log. Now the next one is going to be the same thing as saying 6 times the integral of 1 over x plus c. I'm sorry, not plus c. Right? All right, so this is the same thing as the integral of 6 over x. And so this would yield 6 natural log of x plus our constant c. That is called the constant of integration, by the way. All right, so now breaking off of just your x to the n derivatives. Let's think of antiderivatives. Let's think about some of our other ones. The antiderivative of cosine of x would be sine of x plus c, because the derivative of sine is cosine. The antiderivative of sine would be negative cosine of x plus c, because the derivative, the derivative of cosine would be negative sine, and negative sine would give us the sine right here. All right, the integral of e to the x dx, which means the antiderivative of e to the x, is e to the x, because the derivative of e to the x is also e to the x. The antiderivative of secant x tangent x dx is equal to secant of x plus c. Now this one, we don't use this very often, and so one of the things you need to do is recognize this as something besides what we were working with over here, and it's not the x to the n antiderivative. This is your antiderivative for tangent inverse of x. So make sure you recognize these antiderivatives. The next one here is your antiderivative for sine inverse of x. And then when you have something like this, what you may want to do is actually multiply this together. 2x plus 1 times 2x plus 1, which would involve distributing all that, which would give you the integral of 4x squared plus 4x plus 1 dx. Now, when you have a situation like this, you've got more than just the integral of one term. You've got the integral of several terms in here. You do it the same way, and this is equal to the integral of the first term plus the integral of the second term plus the integral of the third term. All right, so what that's going to yield then is the integral of 4x squared would be 4x cubed over 3 plus, and then you're going to have 4x squared over 2 plus x plus c. And what I would do is I would reduce 4 over 2, which reduces to just 2x squared. All right, so on a problem like this one, what you want to do here is say, whenever you have a polynomial which is more than one term over a monomial which is just one term, you can separate this into 3 fractions. So this would be the same thing as saying the integral of 3x cubed over 2x plus 2x over 2x minus 1 over 2x. So these two things are exactly the same thing. Well, what I want to do now is let's reduce these fractions. This would be equal to 3x squared over 2, because one of those x's will cancel out. This would be plus 1, and this would be minus, and then what I'm going to do is bring the x to the numerator, which will make this x to the, no, I take that back, let's not do that. We're just going to leave this as 1/2 x dx. I'm sorry, not 1/2 x. 1/2x dx. All right, so just for the sake of doing some of this, I'm going to show you this is the same thing as saying 3/2 times x squared plus 1. I'm sorry. Let me back this up. I wanted to separate these. This would be x squared dx plus 1 dx minus 1/2 integral 1/x dx, which means this coefficient does not really have a lot of impact on calculating the antiderivative, other than you're going to multiply this coefficient by what you get from the antiderivative of your variable. So this ends up being then 3/2 times x cubed over 3. This would be plus 1x minus 1/2 natural log of x, once again, plus c. And over here, the 3's will cancel. And so you just end up with x cubed over 2 plus x minus 1/2 natural log of x plus c. Now, most of the time you don't go through all those steps, but mentally that's the process that you are using. So in this case, I would convert the radical, so make it 3x raised to the 3/4 power plus 7x to the negative 5 plus 1/6 x to the negative 1/2 dx. Now really the only time that you want to keep this x in the denominator down here is when it is x to the first power, because x to the first power means you cannot bring it up and make it x to the negative 1, because then you can't do the antiderivative of that. When you have x to the first power in your denominator, that is always going to end up being this natural log of x. And just real quick, I forgot to put the absolute value bars on there, so I'm going to go ahead and do that. All right, so doing the antiderivative here, you're going to add 1 to the exponent, which means you're adding 4/4, giving you 7/4, and that would be over 7/4, plus 7x to the negative 4 over negative 4, plus 1/6 x to the positive 1/2 over 1/2 plus c. And then we simplify this thing. Dividing by 7/4 here is going to be the same thing as multiplying by 4/7. So if you multiply 3 by 4/7, that's going to give you 12/7 plus a negative here, so it's just going to change to minus, and this will be 7 over 4x to the 4th, and plus, now down here, 6 times 1/2 is going to give you a 3 for your denominator, so you're going to get x to the 1/2 over 3 plus c. And then the last problem here, last two problems. Integral here is going to give you 5t raised to the 4th power over 4 minus 10t to the negative 5 over negative 5 plus 4t plus c. And notice that I am using t's this time because we have t as our variable. Okay. And really, I mean, you can leave it like this, but another thing you may see it as, a lot of times they will reduce the negative exponents and move them to the denominator. So over here we got a couple of things. Minus a negative would change that to a plus. 10 over 5 is 2 over t to the 5th power, and then plus 4t plus c. And then lastly, the integral of dy, you can think of this as a 1 right here. The variable that this is being integrating, the variable that we're integrating here is with respect to y, which means our answer for the antiderivative of 1 is not 1x, it is 1y, and then plus c. So hopefully you learned a little bit about your integrals and how you find them. Remember, all you're doing is finding the antiderivative, and that antiderivative represents the area between the curve and the x-axis.